Well, I have the first part of chapter 14, 14.1 through 14.3, and I'm ready to make the video for that. So this is for those AP Chem students out there that want some lecture on chapter 14. We just came out of chapter 13, which was equilibrium, and now we're going to see how equilibrium makes a difference in acid-base reactions. You may recall from Chem 1 that some acids and bases are strong, which means they completely break into ions. They completely ionize in case of acids or dissociate in case of ionic bases. But some are strong and have complete reactions. Of course, we know by now that that means that the K is very large. And so we just assume that the reaction lies 100% to the right. But other acids and even some bases are considered to be weak, meaning that their interaction with water to generate ions is only partial. They get some of their molecules broken into ions and ionized, but at some point the reverse reaction catches up to the forward reaction, and you don't have 100% of your molecules ionized at any one time. So we're going to be looking at strong and weak acids and bases and taking a look at how equilibrium can help us understand the behavior of acids and bases. So to start with, let's remind ourselves what acids and bases are. Acids actually the word acid comes from the Latin word for sour. Acidus, A-C-I-D-U-S, is Latin for sour. And acids do have that characteristic taste. Not that we go about drinking or tasting laboratory acids, but we do have a number of acids in our food: citric acid, acetic acid, and vinegar. And these do give sour taste to our foods. So acids taste sour is one characteristic of an acid. If we go on the other side and talk about bases, kind of an old-fashioned word for bases is alkali. Hence the term alkali metals, alkaline earth metals, alkaline batteries, acid batteries. You know, we have different kinds of batteries. Some have acids, some have bases. Alkalis or bases will have the characteristic of tasting bitter. So if you had some lye soap, which is made by adding base to animal fat, you would the whole thing of mom making you wash your mouth out with soap was that she knew that the soap tasted bitter, and that was an unpleasant taste. So that was a punishment when you had to wash your mouth out with soap because it tasted bitter. These are actually areas on your tongue. There are areas on your tongue where you have taste buds for sour taste and bitter taste. But acids taste sour, bases taste bitter. Now, if we look at a more chemical definition for acids and bases, we could start with the Arrhenius concept. This is the oldest, or one of the oldest, ideas of how to define acids. Of course, at one point, acids were defined as things that contain oxygen, which wasn't very accurate. But the Arrhenius concept is actually a fairly useful concept for acids and bases. In fact, it is the one that we generally use in Chem 1. The idea of the Arrhenius concept, Svante Arrhenius from the 1880s, his concept was that acids, when they are placed in water, they ionize to produce hydrogen ions, H plus ions, and that when bases are added to water, they produce hydroxide ions, H plus ions, hydroxide ions. Put them together, H plus, OH minus, ends up being HOH, or water. Hence the idea that acids and bases neutralize each other. They react to make water. Acids make H plus, bases make OH minus. Together they make water. Acid plus base makes water. So that was the Arrhenius concept. Now, that concept is actually not the definition that we tend to use in AP chemistry, though. So in AP chemistry, we attempt to be a bit more sophisticated about how we define acids and bases. So we use the 1921, something like that, definition by Bronsted and Lowry. or sometimes just called the Bronsted definition. Some people call it the Bronsted-Lowry model of an acid-base. And the idea here is that acids have the ability to donate H plus ions. So you actually say an acid is a proton donor. Bases have the ability to accept H plus, so they are called proton acceptors. Now, in the case of being in water, the H plus ion is really not going to be found individually in water. When H plus is in water, the H plus will be attached to the water molecule to form H3O plus. So H3O plus is called hydronium. So acids, when we talk about the ion for acids, there's really three ways to call it. Three terms could be used to describe it. That would be, we could call it a proton, because you take an electron off a hydrogen atom, that's all that's left is a proton. So an acid is a proton, or you could say, okay, I don't want to say proton, I want to give a chemical formula, call it H plus. Or if you want to be completely accurate and not take a shortcut, you could say H3O plus, because technically H plus dissolved in water is going to be in the form of H3O plus, called the hydronium ion. So to illustrate this idea, we have an acid HCl. Notice the H here in red. That H is going to be donated not as a hydrogen atom, but as an H plus ion to the water molecule. So we normally don't think in Arrhenius concept of water as being a base, but in this case, the H plus is being donated by the acid HCl to the water molecule. So in this case, water is in fact acting as a base because it's a proton acceptor. And so H plus added to water, notice you get a single bond. One of those lone pairs on oxygen ends up becoming the single bond to the hydrogen ion. And now you have H3O plus. And Cl minus is the leftover ion. Cl minus would be chloride, and that would be the other ion formed. So the addition of the acid to water is the formation of the hydronium ion H3O plus and the Cl minus ion. Now, if we think of this in equilibrium terms, we would ask, well, what happens for the reverse reaction? Because we know that all reactions have some degree of reverse reaction. It is very negligible in the case of HCl. HCl is a very strong acid, and it ionizes nearly completely. But if we consider the reverse reaction is that hydronium would be donating H plus to chloride to return to the form of water and HCl on the left. So in that case, hydronium would be acting as an acid, and the chloride would be acting as a base, because the hydronium, if we're looking at this reaction in reverse, the hydronium is donating a proton to chloride, and chloride is accepting the proton. So by the Bronsted-Lowry definition, in the reverse direction, hydronium is an acid and chloride is a base. Now, it's not too hard to see that the base, water, on the left is simply the hydronium ion on the right without the H plus. So if you take the water on the left and add the H plus, you get the hydronium. If you take the H plus off of hydronium, you get the water. In a similar way, HCl on the left has the H plus ion, Cl minus on the right does not have it. So if you put the H plus on the Cl minus and make Cl minus be a base, then the HCl that forms could be an acid, because then it could donate H plus. So HCl is an acid because it can donate H plus. Water is a base because it can accept H plus. Hydronium is an acid because it could donate H plus in the reverse direction. Cl minus would be the base because it's accepting H plus. Now, if we think of the things on the right and the left that are related to each other, the HCl is related to the Cl minus by the fact that HCl has the H plus and Cl minus doesn't. The water is related to the hydronium by the fact that the water doesn't have the H plus and hydronium does, but otherwise they are the same chemical species, just one of them has H plus and one of them doesn't have H plus. So we think of kind of like what we do in English or in Spanish or other languages when we conjugate a verb. When you conjugate a verb, you're simply changing the verb to its other form. Maybe you're taking a present tense verb and you're changing it to its past tense. You're changing the tense of the verb. Well, in a similar way, we are changing the form of a chemical molecule by adding H plus or taking it away. So we're going to call this conjugating. A conjugate a base, or we make the conjugate acid of a base by putting an H plus on it. You make the conjugate base of an acid by taking H plus off the acid. So we would say in this particular example here that the HCl acid has a conjugate base Cl minus. The water, which is a base, has a conjugate acid H3O plus. Or we could say that HCl and Cl minus are a conjugate acid-base pair. Or water and hydronium are a conjugate base and acid pair. So that's the terminology used when describing the Bronsted-Lowry model, is that each side of the reaction has acids and bases, but the conjugate pairs are the ones that differ by H plus. So practice with that, saying something like, okay, what would be the conjugate acid of water? Okay, well, if water has a conjugate acid, to make an acid with water, I would put H plus on it, because then it could donate H plus. So hydronium is the conjugate acid of water. So in the Bronsted-Lowry concept, acid-base reactions are always looked at as reversible, and the conjugate species are the ones that vary by the loss or gain of a proton. So if we take it as sort of a generic reaction, we'll call A any particular anion that could pair up with H plus and form an acid. HA, an acid, plus water, a base, makes H3O plus, the conjugate acid, and A minus, the conjugate base. So this could be HCl, it could be HBr, it could be HNO3, it could be HF, a lot of acids this could be. But the general reaction is that the reversible reaction between the acid and water is that the acid acts as an acid and donates a proton to water, the base, forming the conjugate acid hydronium and the conjugate base A minus, which would be the anion. Now, since this is an equilibrium reaction, we should know how to write the equilibrium expression for this. So, and we call the K for this, we call it the acid ionization constant. Some books, in fact, I think Zumdahl sort of bleeds into doing this and calls it the acid dissociation constant. I prefer, since acids are molecules, not to say that they dissociate, but that they ionize. So the acid ionization constant or dissociation constant is that the K sub A, now we're using another subscript here, letter A for acid here, Ka equals H3O plus's molarity times A minus's molarity over HA's molarity. So you may notice here that looks like Mr. Koker forgot to put water on the bottom. Well, no, I didn't. Water is a liquid. As a liquid, it's not aqueous, it's not a gas, it does not belong in the equilibrium expression because water has a constant concentration of 55.5 moles per liter, and so I can move it over to the Ka side and not put it in the equilibrium expression. So Ka equals H3O plus times A minus over HA, or sometimes we shorten this all down, and instead of calling it H3O plus, we call it H plus times A minus over HA, which would be what it would be if you simplified the reaction by taking water out of it and just said, okay, HA breaks up into H plus plus A minus. So you can either do the long form where you include the water and you add the H plus to it and you make hydronium, or if you want to kind of cut to the chase, you can say The HA molecule ionizes to make H plus and A minus, and it's reversible, and Ka equals H plus times A minus over HA. So generally, we do this the quicker way when we're solving problems, but then we remember that H pluses really don't occur in water unless they are attached to water molecules to make hydronium. Now, the Bronsted-Lowry concept actually would allow you to talk about acid-base reactions occurring outside of water. Now, we always think of acids and bases as being dissolved in water, but technically the Bronsted-Lowry concept says that an acid is a proton donor and a base is a proton acceptor. If we think about the reaction between the two gases, HCl and NH3, NH3 has an unshared pair that can bond to H plus, and HCl has a weak bond between H and Cl, and so in fact NH3 plus H plus could form NH4 plus, and the Cl could become Cl minus because HCl would be donating a proton to NH3. At that point, those two ions, ammonium and chloride, would form an ionic solid, and you get little bits of solid in the air, and those would look like white smoke because ionic crystals are little white crystals. And so you're actually not making a gas, you're making a smoke above bottles of concentrated HCl and NH3 with their lids off here on the right. That smoke is actually little bits of NH4Cl ionic solid formed by the acid-base reaction, the proton transfer reaction between NH3 and HCl. Now let's talk a little bit about acid strength. We sometimes say that certain acids are strong and that others are weak. What we really mean by that, since we know from chapter 13 that everything is an equilibrium reaction, what we really mean by that is that the strong acids are ones that have equilibria that lie far to the right, or in other words have large Ka values, and weak acids are ones in which the equilibrium lies far to the left, which have small Ka values. And so strong acid simply means that we generally assume they're 100% ionized because their Ks are very large, and weak acids are considered to be much less ionized and only partially ionized at equilibrium because their Ks are small. You can also have acids that have more than one ionizable hydrogen. For instance, H2SO4 is called a diprotic acid because two protons can be removed from it. If you dissolve H2SO4 in water, the first H plus that comes off will create H plus and HSO4 minus, but the HSO4 minus ion, hydrogen sulfate ion, has the ability also to ionize and make H plus SO4 minus 2. So I'd like to briefly address the sulfuric acid molecule because there's a bit of an inconsistency between how most colleges will teach H2SO4 and how AP teaches H2SO4. When I first started teaching AP chemistry, it was always a big deal was made about the fact that H2SO4's first H plus is considered strong, and the second H plus is considered weak. And if you're doing anything with net ionic equations or whatever, you have to distinguish between strong acids and weak acids. Strong acids are fully ionized, and weak acids are generally in the molecular ion form and not broken into parts in a net ionic equation. So we made a big point of H2SO4 being a strong acid, but HSO4 minus, the second proton, being a weak acid. I believe Zumdahl in his textbook still kind of holds to that idea, which I think is the more accurate idea of first proton strong, second proton weak on H2SO4. Though last few AP conferences that I've been to, there's been a general shift in the way AP handles H2SO4 in that they generally treat both H's as strong. Now, I don't agree with it. I don't think it's right to say that both H's on H2SO4 are strong. You can prove it with the math that it's not the case. However, for the sake of simplification, I think, to make AP more simple, they've decided that if we're going to call H2SO4 a strong acid because the first H plus is strong, we're not going to confuse students by saying the second one's weak. If we're going to call it a strong acid, we're going to call it a strong acid, and we're going to assume that both protons are strong. So the assumption in AP chemistry is generally that both H pluses on H2SO4 come off 100%. But when you get to college, you get to a more sophisticated approach to it. It's the first H plus that comes off 100%. The second H plus only comes off partially. Okay, I'll get off my soapbox about that. But the important thing here is that H2SO4 is called diprotic because it has two H pluses. Now HCl, we would say, is monoprotic. It only has one H that it can donate in an acid-base reaction, so HCl is called monoprotic. H3PO4, phosphoric acid, that's an example of a triprotic acid. H3PO4, even though all three H's are weak, it does have the ability to give off three H plus ions. H3PO4 is triprotic. A more general term for anything that can give off, that's not monoprotic, that can give off more than one ionizable hydrogen, we call it polyprotic. Polyprotic, more than one hydrogen ion being able to come off of the same molecule. For example, citric acid that's found in citrus fruits, it's triprotic, it's polyprotic, it has more than one proton that it can donate. Let's talk briefly about oxyacids. You find that a lot of acids do contain oxygen, although not all do, but many of them do. You think H2SO4, sulfuric acid, has oxygen in it. HNO3, nitric acid, has oxygen in it. So there's a number of acids, H3PO4, that have oxygen in their molecules. And what you're going to expect to see in that case is your hydrogen will be attached to the oxygen atom. So in oxyacids, acids that contain oxygen, expect the H plus to come off of the oxygen atom and not be attached to, say, the nitrogen in nitric acid. In nitric acid, you have the N in the middle and three O's branching off, and then an H coming off of one of those O's, not the H attached to the N. So expect hydrogen to be attached to oxygens when you have oxyacids. Now, one example of an oxyacid is organic acids that contain this particular functional group called the carboxyl or carboxylic acid functional group. You have some carbons, and on the end of the chain of carbons, you have a carbon with a double bonded oxygen and a single bonded O, single bonded to an H. So you have a double bonded O and an OH. The H attached to the O can be acidic, it can be donated, and so it's a labile proton, we would say, Labile, the labile proton, the proton capable of being donated here, is the H on the OH of the carboxyl group. And if that one is donated or lost to make H plus ions in water, maybe you make H pluses attached to waters, you will be left with what's called the carboxylate anion. So the C and the two O's without the H plus. So this is one way that organic molecules like citric acid or acetyl salicylic acid found in aspirin and other kinds of organic acids, this is the main way that carbon-containing molecules, organic acids, form acids, is by having this particular arrangement of atoms, a C double bonded to an O and an OH group, called the carboxylic acid group. Important to note, all organic acids are weak. So there are no strong organic acids, only weak organic acids with small Kas. So it might get confusing. How do I know that an acid is strong? How do I know when it's weak? Because if it's strong, I'm supposed to assume that it's 100% ionized. If it's weak, then it's not going to be very ionized. How do I know which one is which? Well, there aren't that many that are strong. There's about 7. If you know the 7 strong acids by memory, if you've memorized the 7 strong acids, if it's not one of those, you can assume it's weak. It's probably the simplest way to do it. So just memorize the 7 strong acids. Memorize that hydrochloric acid is practically 100% ionized in water. So is its cousins, hydrobromic and hydroiodic. Interestingly here, HF is not. HF is actually weak. So HCl, HBr, and HI strong. The oxyacid, chloric acid, HClO3. So ClO3 minus chlorate bonds to H plus to make chloric acid, HClO3. Perchloric acid, HClO4. These two oxyacids are both assumed to be 100% ionized in water. Nitric acid, another oxyacid, also considered strong. And sulfuric acid, generally grouped with the strong acids to memorize. Now remember, just to review, H2SO4 from AP Chemistry's perspective can be assumed to be doubly strong, that both H's are strong. When you get to college, though, your professor will probably want you to know that H2SO4, only the first H plus is strong and the second one is weak. And here is actually right at the top of this chart support for the idea that the second H plus on sulfuric acid is weak. When you take one H plus off of H2SO4, you get HSO4 minus. The Ka for HSO4 minus is less than 1. It's 1.2 times 10 to the minus 2, 0.012. So that's telling us that with a small Ka like that, HSO4 minus is a weak acid. However, most weak acids are even smaller than HSO4 minus. Of the weak acids, it's one of the stronger ones because its Ka is larger than most Kas for common monoprotic acids or acids that donate 1 proton. HSO4 minus 1.2 times 10 minus 2, practically exactly the same. Strength of acid, chlorous acid, HClO2 has a 1.2 times 10 minus 2 Ka value at room temperature. Add a chlorine to acetic acid and you get 1.35 times 10 to the minus 3. Hydrofluoric, 7.2 times 10 to the minus 4. Nitrous acid, regular acetic acid, 1.8 times 10 to the minus 5th. Probably my favorite example to use if I'm just making up an acid equilibrium problem is I'll probably pull acetic acid out and say, okay, let's assume acetic acid. Interestingly, aluminum 3, Al plus 3. Al plus 3 dissolves in water and is surrounded by 6 water molecules in a hydration sphere. Remember that waters surround ions in water? That hydration sphere, because of the pull of the plus 3 ions on the water molecules, it actually weakens the bond between the oxygen and the H's on the water molecules. And so the hydrated aluminum ion, the aluminum ion with 6 waters attached, has the ability to donate H plus because the way the strong and small highly charged plus 3 ion, very small plus 3 ion, bonds very strongly to the partial negative of the oxygen in water, and that pulls electrons away from the OH bonds, which then make them weaker, so H plus can be pulled off. Hydrated aluminum 3 ion. It's actually acidic, 1.4 times 10 minus 5th. Hypochlorous acid, hydrocyanic acid, HCN. CN minus is called the cyanide ion, so we call it the hydrocyanic acid. the ammonium ion. Ammonium, that's the conjugate acid of ammonia. Ammonia must be a base because NH4 plus, its conjugate acid, is an acid with a value of Ka of 5.6 times 10 minus 10. Now here's an example of an organic acid, albeit very weak, that does not have the carboxyl group on it. It's actually phenol, which is a benzene ring with an OH group on it to make it an alcohol. Phenol, that benzene ring with an OH, the H on that O does have slight acidic properties and a Ka of 1.6 times 10 minus 10. Now, if we think about an acid having a conjugate base, then we have a general relationship that the stronger the acid is, the weaker its conjugate base. The stronger the acid, the weaker its conjugate base. If you think about it in terms of competition, in the forward direction, the acid is donating the proton. In the reverse reaction, the base is accepting the proton. And so if you say that your acid really wants to get rid of the proton, then the conjugate base of it really doesn't want to gain that proton. So the stronger your acid, the stronger the tendency for the acid to give up the proton, the weaker the tendency for its base to accept that proton back. So you think of its conjugate base and the weak acid. So in the case of acetic acid, I have pictured here the acetic acid molecule. It's got a carboxyl group, because you can see on the left there, top left, that it's got a carbon double bonded to an oxygen, single bonded to an OH. The H is in green here because it is the ionizable or labile proton. That labile H plus is going to add to water to make hydronium on the right, and you're going to lose that H plus and you're going to form the acetate ion, C2H3O2 minus. In the reverse direction, that proton is going to add to acetate, so acetate's going to be a base and hydronium is going to be an acid and make the acetic acid. But the easier it is for the acid to give up the proton, the harder it is for its conjugate base to accept a proton. So if you were selling something at the garage sale because you really didn't want it anymore, then you would be saying that it's easy for me to give up this this particular item that this old DVD that I've watched 5 times and don't really like the movie. It's easy for me to sell and give up this DVD. So you sell that DVD at a garage sale. Well, the next time you go to a garage sale and you see that DVD, you're not going to buy it. You just sold one at your garage sale. So the greater the tendency for an acid to give up H+, the larger its Ka, the weaker the tendency of its conjugate base to accept H+. So now down here on the bottom, we actually see ammonia acting as a base, accepting H+ from a water molecule to form ammonium and hydroxide. I didn't check this picture. It should have a backwards arrow because ammonium can give H+ to hydroxide to form ammonia plus water. So in this case, ammonia would be a base, water would be an acid, NH4 plus would be its conjugate acid, and OH minus would be its conjugate base. And so if we look at NH3 and NH4 as being a conjugate base and acid pair, the weaker the ammonia, the stronger the NH4 plus, or the weaker NH4 plus is, the stronger NH3 is. Now it's interesting here that in the first reaction we see water acting as a base accepting a proton from acetic acid. But in the second reaction we see water acting as an acid and donating a proton to NH3. So in this case, actually, water is both shown here as being able to be an acid or able to be a base. There are some species that can do that, some species, some chemicals that can donate protons or accept protons, either one, and those are a group of chemicals we call amphoteric. So if a chemical has the ability to add H plus to its formula or give up H plus from its formula at the same time, like water can give up H plus and form OH minus, can add H plus and form hydronium, we say it's amphoteric. And in fact, water has the ability to give H plus to water and accept H plus from another water. It's called the autoionization of water. It only happens about 2 molecules per billion in water, but it does occur. We think of pure water, we think, okay, water is a molecule, there are no ions. But in fact, even pure, totally pure water has a few ions, about 2 per billion, due to the phenomenon known as autoionization or self-ionization of water, water molecules ionizing other water molecules. So if you think of 2 water molecules, one able to act as an acid and the other to act as a base, one accepts a proton and becomes hydronium, the other donates a proton and becomes hydroxide. And so you get your conjugate acids and bases on the right side for water. So water ionizing in water to form hydronium and hydroxide, the water molecule has the ability to split into H plus and OH minus. That reaction is actually the basis of the pH scale. So let's take a look at this autoionization of water, and we're going to tie it into the pH scale in just a minute. The K for the autoionization of water is given, and we just love to put subscripts on K's. We call it Kw for water ionization. In pure water at 25 Celsius, the Kw number for the autoionization of water is 1 times 10 to the minus 14. Very small K. In other words, 2H2O liquid yields H3O plus plus OH minus. The Kw will be the concentration of OH minus times the concentration of H3O plus. We ignore the concentration of water because it's a pure liquid, so it's not in the K expression. 1 times 10 to the minus 14 equals OH minus times H3O plus. Of course, in pure water, where there's been no addition of H plus or OH minus, you have an added acid or base to it. In pure water, the H plus or H3O plus and OH minus will be equal, which means in pure water, the OH minus concentration will equal the H3O plus concentration, and they'll each be the square root of 1 times 10 to the minus 14. Or in other words, 1 times 10 to the minus 7. Oh, there's that 7 from the pH scale. So this relationship, OH minus equals H3O plus equals 1 times 10 to the minus 7 in pure water, we can actually see that this autoionization of water equilibrium can be shifted left or right by the addition of OH minus or H3O plus to water. So when you add an acid or a base to water, you shift the equilibrium between water splitting into H3O plus and OH minus. In a neutral solution then, H plus equals OH minus, which equals 1 times 10 to the minus 7 molar. But in an acid, the H plus is going to be much greater than the OH minus, because the two numbers multiply to give 1 times 10 to the minus 14. If the H plus is bigger than 1 times 10 to the minus 7, then the hydroxide has to be smaller than 1 times 10 to the minus 7. So we get this inverse relationship. The more H plus you put in water, the less OH minus there will be in water. The more OH minus you put in water, the less H plus there will be. Quick math problem. What's the hydroxide ion OH minus concentration if your solution is 0.1 molar H plus? So our relationship Kw, H plus times OH minus equals 1 times 10 to the minus 14. If the H plus is 1/10 of a mole per liter, so you've got some 0.1 molar, say, strong acid, then 0.1 times OH minus will be 1 times 10 to the minus 14. Divide both sides by 0.1. The OH minus is 1 times 10 to the minus 13. So the H plus grew to 0.1, 1 times 10 to the minus 1, but the OH minus is now 1 times 10 to the minus 13. So that would be an acidic solution because it has much more H plus than OH minus. If we put a base in, if we made a basic solution, then your OH minus concentration would be greater than your H plus. And this can be many powers of 10, greater or less than. So the H plus and OH minus's molarities can vary by many, many orders of magnitude or powers of 10. This little diagram shows that when you have a lot of H plus, you have very little OH minus, and when you have a lot of OH minus, you have very little H plus. If the H plus is 10 to the 0, which would be 1 mole per liter, just 1 mole per liter of a strong acid, 10 to the 0, the OH minus will only be 10 to the minus 14. If your H plus is 10 to the minus 7, it's neutral, then you have OH minus 10 to the minus 7. If your H plus is 10 to the minus 14, then your OH minus will be 10 to the 0. So you can kind of see that we've been scratching around on the edges of the pH scale. The pH scale, which actually stands for the power of hydrogen ion, that's why it's a lowercase p and an uppercase h, power of hydrogen, pH. The pH scale, the power there doesn't mean strength, it means exponent. And that's why we use logarithms on the pH scale. The pH is actually the negative of the log base 10 of the H plus ions moles per liter. So H plus moles per liter, take the log of it, take the negative, you have the pH. So if we think of that pure water, remember what the H plus moles per liter was in pure water? H plus was 10 to the minus 7. The log of 10 to the minus 7 is negative 7. The negative of negative 7 is positive 7. The pH of pure water is 7, neutral. Of course, if you want to find the H plus from the pH, you need to take H plus equals 10 to the minus pH. If the pH is 7, the H plus is 10 to the minus 7. If the pH is 1, the H plus is 10 to the minus 1. Now, usually we work from the pH scale, but you could turn it around and work from a pOH scale. And so pOH would be the negative log of the OH minus concentration. Or the OH minus concentration would be 10 to the minus pOH. So it's the less common of the scales to work from, but pOH is another way of describing how much acid or how much base there is in water. Now, since, remember, Kw is H plus times OH minus, which equals 1 times 10 minus 14, then we could say pKw, putting a p in front of it just means taking its negative log, pH, negative log H plus, pOH, negative log OH minus, pKw, negative log of Kw, pKw equals 14. And there's a relationship here. Because H plus times OH minus equals 10 to the minus 14, pH plus pOH equals 14. To illustrate that, let's say we have a pH of 4. pH 4. That would mean pOH would be 10. 4 plus 10 equals 14. So let's look at that. pH 4. That means the H plus is 10 to the minus 4. If the H plus is 10 to the minus 4, the OH minus is 10 to the minus 10, and the pOH would be 10. So now 4 plus 10 equals 14. So the math here is logarithms. As long as we stay on whole numbers, you'll be able to do fine without a calculator, but when we start to get into decimal pHs, you'll want your calculator for this because you can't really take logs of things that are decimals without a calculator. So let's do an example out of the book here about pH and pOH. So let's calculate the pH and the pOH for this solution where the OH minus molarity is 1 times 10 minus 3. If the OH minus molarity is 1 times 10 minus 3, the pOH, the H plus rather, is going to be 1 times 10 minus 11. So your pH is going to be 11, your pOH is going to be 3, because the OH minus was 1 times 10 minus 3. I don't think I typed that in there. I should have. Because it did say calculate pH and pOH. The pH is going to be 11. The pOH is going to be 3. And 11 plus 3 equals 14. pH plus pOH equals 14. Now, 1 molar OH minus means Your POH is going to be, okay, 1 molar, 10 to the 0. POH is going to be 0. Your H plus, if the OH minus is 1 times 10 minus 14, so your pH equals 14, so 0 plus 14 equals 14. Now let's talk about doing a decimal of it. Human blood is about 7.41 pH. Let's find the POH, the molarity of H plus, and the molarity of OH minus, because we know the pH is 7.41. 14 minus 7.41, the POH is going to be 6.59. The H plus's molarity, 10 to the minus 7.41. Put it in your calculator, 3.9 times 10 minus 8 moles per liter. The OH minus concentration, 10 to the minus 6.59. 2.6 times 10 minus 7 moles per liter. Now, some of you right now are thinking, wait a minute, Mr. Koker, caught you on a sig fig error. 7.41 has 3 sig figs, and 6.59 has 3 sig figs, but you only put 2 sig figs in your concentrations. No, you didn't. pHs and POHs are special because they are based on logarithms. New sig fig rules. When it's based on logarithms, the decimals are the only part of the logarithmic function that have sig figs. The number in front is based on the exponent. So the exponents aren't sig figs. Only the numbers in scientific notation that come before the times 10 to the minus 8 or the 10 to the minus 7 are the sig figs. So 7.41, the 7 is not considered a sig fig. It's considered an exponent. The 4 and the 1 determine the size of the first part of your scientific notation, and that's where your sig figs come from. So 7.41 actually only has 2 sig figs, the 4 and the 1, which is why I gave 2 sig figs for my H plus ions concentration, 3.9 times 10 to the minus 8. The 10 to the minus 8, that 8 comes from that 7 value being bigger than 7 there. So it's actually into the next power of 10 there. And so we get our 8 from that 7. Similarly, 6.59, we get that 7 from the 6.59. And then with 5 and the 9, determine the 2.6 in the front. Okay? A little weird, but sig figs when it comes to pHs and POHs are the decimals, not the rest of the number, not the number in front of the decimal. Okay, so that's a start there. I tried to give some pretty good detail. Now, if you're looking at it going, Mr. Koker, you're going in a lot more detail than you have in previous lessons. I'm going to have to do that for this chapter because last year, because of COVID, you didn't get a very good acid-base coverage. Without a good acid, see, you would have done acids and bases in April and May if it hadn't been for COVID. And you missed April and May. So that's why I'm going to go into some pretty strong detail on these lectures. And I'm going to encourage you to really listen well, jot down questions, and ask questions in class because we need a good, strong foundation of acid-base chemistry. Acid-base chemistry is probably 20% of the AP test. It's like a fifth of the AP test. You need a strong foundation in it, and you didn't get a good coverage of it last year because of COVID. So power through. We're giving you 2 full weeks here to handle chapter 14, but do take the time to learn this acid-base chemistry well. And I will be posting more videos for chapter 14, starting with 14.4, as soon as I can get the PowerPoints made up and the videos recorded. All right, so thank you very much for your attention. I'll get this thing turned off.